Hello everyone. So today I'm going to go ahead and talk about PhET. It's one of the many one of the many topics that you'll look at in terms of basically in chemistry in terms of electrons and molecules and like their shapes. So VSEPR. So right, does everyone know what VSEPR is? Cool. Okay. So this is just essentially shapes, geometry. We're going to look at molecular and electron geometry. I'm going to use a simulator to kind of explain things a little bit more visually than I would like on a PowerPoint or on the board, because you've already seen that. You've gone to lecture, I would hope, and you've already seen what things look like on the board, what they look like on a PowerPoint. I don't think you guys, if you guys are still confused, clearly that's not helping you. So maybe this simulator will. First off, I'd like to thank the PhET PHET program as part of the University of Colorado in Boulder, or University of Colorado Boulder. They make these awesome, simulators. They're free. You just go to phet.colorado.edu, and basically they have these really cool simulators for every single subject, like chemistry, physiology, biology, physics, you name it. Most likely they'll have it. I learned physics this way, so hopefully you guys can learn chemistry this way. So basically this is what we were looking at with the balloons when Dr. Van Dorn was using balloons to kind of demonstrate that electrons kind of they take a certain shape. In the middle here in the purple, you see that this is we don't really know what kind of element this is. It's just a central atom. Around it, I'm going to add some bonds and lone pairs. We're going to go and explore the different types that are going on here. So I'm going to add, first off, just another atom. We don't really care about electronegativity at this moment, but we just know that there are two things bonded. There are two atoms that are bonded by a single bond here. And we look at the shape here, and it's already linear. We can see that. We have added a lone pair, so nothing else is going on. If I add the lone pair, see how it's still linear? Nothing has changed. So let me go and undo that. I'm going to add another bond. So this essentially, and actually you can see the angle now. The angle between these two atoms, so essentially the angle of this central atom is 180. We're still linear. This proves that what we're talking about in class is actually real. There are no lone pairs here, so there's no need for anything to bend or that sort, but let's go ahead and change that. Let me go ahead and add a lone pair. I add the lone pair, right? So that's just two electrons, and we bend at 120. If I move this way, do you see how everything else just kind of moves to kind of adjust? If I move it close enough, it just readjusts. Basically, this shows that electrons will repel each other, just like two positive or two negative sides of a magnet. They'll repel each other. There's no way of connecting two negatively sided magnets. Same thing here with electrons. Electrons are negative, so two negatives won't go together. They're pairs like that, sure, but when you try to attract two, it's just not going to work. Two other electron groups, it's not working. See, they're just gonna repel. There's no use. I could do this all day. If I had another a lone pair, see how we've bent it a little bit more? I'll do that one more time. So I'm going to go ahead and actually remove that lone pair. I'm going to add it again. We've kind of bent it a little bit because this extra lone pair needs that room. It needs that space. So we're going to actually bend it so it's going to be smaller in degree. If you look at it prior, the electron geometry changed to trigonal planar, and the molecular geometry turned to bent. So with electron geometry, the difference here is that for electron geometry, we count these lone pairs. We count them for something. In this case, it's just, one groups, two groups, three groups, so it's trigonal planar. However, for molecular, we don't really look at that, the lone pair. So we ignore it. If it's at the bottom, let's just ignore it. This is bent, simply because it's not linear, because this lone pair is repelling these. It's actually squishing these. If I try to make it linear, it's not working, right? Because the lone pair is actually squishing these two white atoms together. So because it's doing that, there's no possible way that these two will become a linear 180 degree item. It's going to stay at 120 degrees. Hopefully that kind of makes sense. If I had the other lone pair, I'm still bent, but I have a different bond angle. And the reason why I have a different bond angle is this bond angle represents an angle of a tetrahedral. So, and we have two lone pairs here. That make pretty good sense? Hopefully it does. If not, I would definitely go onto this website and play with the simulation if you don't really understand what I'm talking about. But this is pretty simple, guys. Nothing really too difficult here. I'm going to go ahead and get rid of the lone pairs, make it linear again. I'm actually going to make double bonds now. So this resembles a molecule you guys already know. And if you don't know what that is, let's talk about CO2. If this was C and these were two oxygen atoms, this is linear. There's no lone pairs here. It's perfectly linear. It doesn't have to bend because there's no lone pairs required. However, if this was something like SO2, right? Sulfur has 1, 2, 3, 4, 5, 6. 6 valence electrons. So I need to add a lone pair. If I do that, we have our bending action again. Even though we have the double bonds, this electron pair will trump what a double bond does. We don't do bond rotations. This cannot really rotate that much, and basically the lone pair will start pushing these, and same thing with the single bonds. It's going to push it so that it has its own space. It's like the baby of the family. When you get a new kid, he just takes up all this space, you know? So basically the younger or the middle child and the older child kind of have to move and, like, you know, bend ways for this new child. If that kind of made sense. Sorry if I sound like a complete lunatic. If I had another lone pair, generally there are some places where this does exist, and same thing, the bond angle turns back into 109.5. If you've been looking at the geometries, which I've showed, we go from this linear atom, or we go from the linear molecule, we go to this trigonal planar and bent molecule, and then we go to tetrahedral. And every time we get a smaller bond angle, and we see it change. Now I'm going to go ahead and actually now add triple bonds, because why not? Triple bonds are fun. And actually, let's make it more fun. Let's add triple bonds on one side and double bonds on the other side. We're still at 180, right? Lone pairs are the important part. If you notice, even if I add one lone pair, we still bend to the same thing. Basically, this shows that you have to count lone pairs for some kind of bonding item in tetrahedrals, and you have to count them in terms of the movement and shape of this molecular geometry. However, it's still bent, right? We're looking at not the shaded part. So basically, this is what we're looking at. We're looking at bent. When we're looking at electron geometry, we're looking at this, which is a tetrahedral. This is no different than me doing this, right? Tetrahedral, 109.5. Right, if I want to add more, I can. And this is crazy. I don't think you really have to know this, so don't worry about that. But this is it. So let's go over like the shapes of everything. That way you know what's going on, or the basic shapes. So this is linear. This is also linear. This is bent with a 120-degree bond angle. I'm looking at molecular geometry, by the way. This is also trigonal planar for electron geometry. This is bent with actually, let's do it over again. Linear. Right, linear. If I add the lone pair, this is bent, but with a 120-degree angle. I remove the lone pair because you need to know that there's only one lone pair here. If I add another lone pair, which you can't see, if I add another lone pair, this is bent, but with a 109.5-degree bond angle. However, the electron geometry is tetrahedral simply because these two are here. Moving on, if I add another bond and remove all lone pairs, we would trigonal planar. Trigonal planar. There we go. Trigonal planar. It's flat, right? It's on a plane. Nothing 3D about it. It's trigonal planar, and it's a 120-degree bond angle. Each of these is 120. Okay, so now this is the tricky part. A lot of people have problems seeing this next one, trigonal pyramidal. If I add a bond to this, do you see how we're no longer in the plane? How this the central atom has kind of raised itself? So I'm gonna show me removing this bond or this lone pair. See the difference here. So I'm gonna remove it, and it kind of flattens. Right? This is trigonal planar. If I add the lone pair, we kind of all these white atoms have kind of moved away to make room for this electron pair. So now we're at a trigonal pyramidal for molecular geometry. And for electron geometry, it's the tetrahedral. Just making sure that's clear. Same thing with, actually, yeah. And then, so this is trigonal planar, trigonal pyramidal, right? Trigonal pyramidal. And then if I add one more bond, but remove all lone pairs, now we have a tetrahedral. This is not the same as your little, when you write it on paper. This is different. So basically, if two of these atoms are different than the other two, you're going to have some kind of dipole moment. You're going to have some kind of polarity, because this is no longer flat. Nothing cancels each other out. In this case, because all these atoms are the same, we're going to call them hydrogens. Because they're all the same, basically there is no polarity. And we'll talk about polarity. Oops. We'll talk about polarity in another video. Sorry about that. But basically, that's really it. There's nothing really too, complex about this. I would hope. If you have any questions, go and please put them in the comments below, or ask a preceptor during office hours. You can ask Dr. Van Doren during her office hours. The preceptor making these videos, my name is Jay. My hours are on Wednesdays, from 3 to 5, I think. Yeah, 3 to 5. You're free to come to them if you have questions about the videos. You are free to ask any other preceptor. Bring the video in and try to have them explain it to you if you don't really get it. But feel free to put something in the comments, or come see one of the preceptors. Primarily come see me, because I made the videos. I know what I'm talking about in terms of the videos. Come see us during right after class or right before class, and I'm happy to explain anything you guys need help with. So this video is all about VSEPR and geometry, electron and molecular geometry. I hope this was very helpful for you. If you have any questions, go and please leave in the comments. Please thumbs up the video so I know you watched it and you liked it. Thumbs down if you didn't like it. And go ahead and email me if you have any suggestions for how I can improve the videos. You're free to put them in the comments as well. No one's going to kill you. Don't be shy. I'm happy to take criticism. So if there's something you don't like, or there's something you do like, put it in the comments. I like to hear things. Thanks for watching. You guys have a great evening, afternoon, whatever. Okay, bye-bye.